In this screencast, we want to list and talk about some important theorems about convex quadrilaterals. This is the obvious one. In a convex quadrilateral ABCD, the angle sum is 360 or less. Should be straightforward. We draw in diagonal AC. We get a pair of triangles. The angle sum for triangle ABC is 180. The angle sum for triangle ACD is 180. And these two angle measures add up to the measure of angle C, and these two angle measures add up to the measure of angle A. And so the angle sum for ABCD is no bigger than 360. It is a direct corollary of the Saccheri-Legendre theorem. It is also true that every parallelogram is convex. Now let's talk about what we mean by that. Every parallelogram is convex. Let's decide what we mean when we say parallelogram. A parallelogram is a quadrilateral with both pairs of opposite sides parallel. Both pairs of opposite sides are parallel. That's the definition of parallelogram. There may be other ways to describe a parallelogram. There may be other properties of a parallelogram. But when we talk about a parallelogram, that's the definition in play. Sorry. Both pairs of opposite sides are parallel. And that's what we're going to use here. So when we talk about what we mean by a convex quadrilateral, let's just drive home what that means. Without loss of generality, I'm going to focus on C. The parallelogram is a convex quadrilateral if vertex C is in the interior of angle DAB. And similarly for the other vertices, if one vertex is in the interior of the rays formed by, for lack of better terminology, the other 3 points, then the quadrilateral is convex. So without loss of generality, we'll focus on C. We'll show that C is in the interior of angle DAB. Now, to do that, we have to show that C is on the D side of AB and C is on the B side of AD. That's the plan. That's the plan. So first, we look at the fact that DC and AB are parallel because they are opposite sides of a parallelogram. C has to be on the D side of AB. C and D have to be on the same side of AB. If C and D were on opposite sides of AB, then the segment between C and D would intersect line AB. But that's not what happens. CD is parallel to AB. It does not touch AB. And if the line doesn't touch, the segment doesn't touch, so C and D must be on the same side of AB. Similarly, oh bugger. There we go. Similarly, AD is parallel to BC, so B and C must be on the same side of AD. Otherwise, the segment between B and C would intersect line AD. This line doesn't intersect that line, so the segment certainly doesn't intersect the line, so C and B are on the same side of AD. And so point C is in the interior of angle DAB, and that argument holds for all other vertices. And so every parallelogram is a convex quadrilateral. And that's great because with a convex quadrilateral, we can draw both diagonals. They're inside the figure. We're fine with that. This is also not too hard to show. ABC is a triangle. D is a point on AB. E is a point on AC. Then BCED is convex. So we would have to show that D is in the interior of BCA, and that's not hard to do. D is on segment AB, and since D is on segment AB, it must be in the interior of angle BCA. Similarly, E is in the interior of angle DBC, because E is on segment AC, so that's not bad either. It is also not too terribly hard to show that B is in the interior of angle DEC, right? Because A is on line EC, D and B must be on the same side of EC. And similarly on the other end, and then you make the same argument for point C. So we can show that that figure is convex. So that's not bad. Couple of quickie results. We can show that ABCD is convex if and only if the diagonals intersect. So in quadrilaterals that are nice, the diagonals intersect, and in quadrilaterals that are non-convex, the diagonals do not intersect. This is an if and only if biconditional, and that can be proven. And then there's this one: if ABCD and ACBD are quadrilaterals, then ABCD is not convex. So if it is possible for you to say, here's A, B, C, D, but here is also A, C, B, D, and that's a quadrilateral. If black and blue are both quadrilaterals, well, that quadrilateral you started with is not convex. And that can be proven. So that quadrilaterals are a little bit more complicated. We don't play around a lot with non-convex quadrilaterals. We much prefer convex quadrilaterals. We much prefer convex quadrilaterals, and there are really, really good reasons for that that'll become clear as we go. Very well.